In this video, let me introduce you with the fundamental differences that there exist between the quantum world and classical world. So the title here is quite clear. It's the quantum computer, but the aim of this video is to make the differentiation between a quantum computer and the classical computer. The fundamental basis of the differences between these two computers, I can say that in quantum computer, the computing operates on the principles of quantum mechanics, while in classical computing, the computation is done on the basis of classical physics in terms of binary logics. Information representation in quantum computing. Quantum computing uses quantum bits, or we call them qubits, which can exist in multiple states simultaneously. And this is basically the result of superposition state. Here, the system can be at multiple states. In fact, between two states, there can be infinite number of states where there is the existence, there is an existence itself. While in classical computing, there are only two binary bits, zeros and ones. So there is a hell of difference between the two computation processes. In quantum computer, there is a long range of information out there, and all that information is the same information is simultaneously present at a large number of states. But that's not the case with the classical computation, because classical computation purely works on bits, that too in the form of zeros and ones. Parallelism. Quantum computing takes advantage of superposition to perform calculations simultaneously. So the beauty of the quantum philosophy in itself is that the computation takes place in a superposition state, where multiple calculations can be carried out simultaneously, and potentially solving complex problems much faster than that of classical computers. Quantum entanglement. In quantum computing, qubits can be entangled. So what's the meaning of entangled here is that it means that one qubit is dependent on the state of another qubit, and enabling the powerful correlation, which is not possible in case of classical computing. So the action of on one qubit can certainly influence the action of another qubit, even though the two qubits have infinite distances between them. The next point is the quantum algorithms. In quantum computation algorithms like Shor's algorithm and Grover's algorithm can be effectively used to solve some specific problems. And these algorithms are they work exponentially and solve the problems which are extremely difficult for classical computers to perform any sort of computation on. The problem of error connection in quantum computing faces challenges with quantum decoherence and errors due to delicate nature of qubits, and this is how there is a need of sophisticated error correction techniques in case of quantum computing. Scalability. should be the next point here. And what is this scalability? Is that quantum computing is still in its early stages. It's baby computing. It's not even the DOS of. It's not even in a state where we will call the DOS of classical computers. So quantum computation is at very early stages, and it certainly faces scalability challenges where classical computers have reached advanced level of scalability and performance, thinking in terms of Moore's law and its proved elegance, as moving on from 18 months to 18 months and 18 months. Now we can see that there is saturation in making use of classical computers. I feel that the time has come when we will not have extra models of mobile phones. We will not have extra models of computers because the classical edge has reached to its level, and it's going beyond that. The laws of physics are totally different, like nanotechnology. So the scalability and performance of classical computers, it is to its saturation, while it has marked exponential applications till now. But on the other hand, quantum computing is still in its early stages, and we don't know where this technology will go. Whether it would be possible to have a quantum computer in real format where it can perform all operations. Hardware differences. So quantum computers are physically different from classical computers, often requiring specialized setups like cryogenic environment for qubit stability, because the small disturbance in a room where there is a quantum computer may change the action that's going on in the quantum computer. It may influence that, but that's not the case with the classical computers. In case of classical computers, we don't need specialized rooms, specialized temperatures, and all that. We can have them in our pockets, and we can use them. Uh, so the current applications, classical computers are widely used in various fields, while quantum computing is still primarily in the research and experimental phase, with the limited practical applications. Not at all the way that there is a large range of applications that we have seen in classical computers. That's not the case with the quantum computer. The future potential. I think that this quantum computing holds tremendous potential to revolutionize industries like cryptography, optimization, and drug discovery, where you don't have to go with hit and trial methods. Suppose there was COVID virus was there, and people were in search of vaccine, but in finding a suitable vaccine to get rid of COVID-19, people had to use those classical techniques where you had to take a large number of cups, and seeing where the optimization will take place, where the result will come, which will be optimized to be used against COVID-19. But that will not be the case if we have quantum computation in its practical form, and there is a possibility that we can guide the quantum computer for having a problem, and it will make its own calculations and will come up with the most probable and plausible solution for the problem, which is not the case when it comes to the classical computers, uh, and to To end this talk, I would say that these points that I talked about, they simply outline the key distinctions between the quantum computing and classical computing, and showcasing the unique capabilities and challenges of each paradigm. Quantum computing continues to advance. It may open up new possibilities for solving complex problems that are beyond the reach of classical computers. Say, for example, string theory is out there, and in string theory, the scientists, the theoretical physicists, they make use of super numbers, and it's impossible for classical computer to make any kind of operation on these super numbers. But when a quantum computer is there in its real domain, it has all those capabilities that it can solve the equations which are accommodating super numbers, and can predict the predictability that might be there